Alright, hey Kev. I'm going to show you the run through for basically an entire simulation setup from geometry to mesh to fluent. Um, okay. I'm going to show you a setup for a steady state simulation because that's just what I'm setting up right now. Um, I'll show you the differences between setting up the steady state and the transient. It's really not that much different. You just select transient and change some settings around, but not too many. Um, Alright, so gonna import your geometry and then open up Design Modeler. Alright, so what I'm gonna do, first of all, I want to do a blade pair, so I'm gonna mirror this. I'm gonna mirror this about the YZ plane, and I'm gonna select the blades. Okay, and then what I'm gonna do is I'm gonna do a translate operation to both bodies. Well, we're gonna have to do it individually because I don't think we can do two-way translation. I'm gonna make this a distance. Okay, wrong way. Okay, and then we're gonna do the same thing to the other one. I think this is about 1.5 inches of space, so we're putting about 3 inches of space between the blades. Alright. Let's see. From here, what we need to do, right, is create our rotating regions. Also, what I'm going to do is I'm going to rotate this blade. Select the XY plane, and then what I'm going to do, oh, sorry, not the XY plane. That's my bad. The ZX, oh, no, the YZ plane. Alright, and then we're going to rotate this 90 degrees. Right, is that the right blade edge? No, we'll go negative 90 degrees. Because I want the trailing edge, or the sharp tip facing the blades, or facing the wind. Alright, so that's the geometry setup. Just for the blades, we're going to create our rotating regions and then our wind tunnel. So I'm gonna work with the XY plane. I actually already have a design here, but you can make it from scratch. Well, basically I'll just show you how to do it. So what you'll do, first thing we're gonna do is we're gonna make this circle. What you'll do is you'll come over to sketching. You'll select the circle option. You can start at the origin and stretch out. You can create a circle of whatever diameter. And then what you can do is you can select dimensions, general, click on the circle and drag it out, and you can set a specific diameter for the circle, and whatever you change it to, it'll generate. When you click generate, it'll regenerate that sketch at whatever dimension you set it at. What you're going to do then is you're going to select modify and go to trim. You're going to cut off the two pieces of the circle here, and in order to do that, you're going to first have to make a line which goes through the center of the circle. After you do that, you're going to go to revolve, which we're going to have to do now. So we're going to go to revolve. We're going to revolve, sketch this half circle that we now have around the, in my case, the YZ plane, and at 360 degrees. and we're going to make sure that in the operation, instead of add material, we select add frozen so that it generates a whole new body and doesn't merge that body with what's already there. Okay, so we created the revolve now, and we have a circle in my case, or a sphere in my case, of a radius of 1.5 meters. And I actually think in this case, for this blade profile, like that's probably too small. So let's go 2 meters, right? So now if I regenerate that, I come back to model, I now have a 2-meter sphere, 2-meter diameter sphere. So design modeler is pretty flexible in how you can sort of mess around with your settings. It does look a little bit outdated, but it's honestly pretty good. So to create this wind tunnel now, you can come back to sketching, create a new sketch on the XY plane. All I did was I created a rectangle from the rectangle tool, just from, you know, whatever, some particular point to some particular point. I cut off this edge using the trim tool from modify, and then I created another circle, which I centered at the intersection between the line that was here and the y-axis, and just extended it until it touched the ends of the rectangles. And then what I can do is just set some dimensions. So I'll set a general dimension on the length of the wind tunnel and the height, and then I will set a vertical dimension from the x-axis to the inlet, or, you know, the half circle here. I'll set these appropriately. So I want, in my case, I want the blades to be, you know, about 3 meters from the inlet, and I like the height of the wind tunnel to be about 4.5 meters and the length to be about 6 meters. From there, what we can do now is extrude the wind tunnel. So we'll come to sketch 6, I'll extrude. Make sure we do add frozen again. Make sure that we do the direction both axisymmetric. And we'll make this about 2 meters worth, about 2 meters tall. 1.75 meters tall. That's appropriate. Okay. Almost done. All that's left now is to create our booleans. So first thing we'll subtract is, I want to target the wind tunnel, and I want to subtract the rotating region from the wind tunnel, and I want to preserve the tool bodies because I want to keep the rotating region. I'm going to rename this rotating region. I'm going to make sure this is selected as a fluid, and I'm going to do the same thing for the wind tunnel. Label it as a fluid. And now we're going to create a second boolean, and we're going to subtract the blades from the rotating region. So the target body is the rotating region. We're going to subtract the blades, and we're going to actually keep preserved tool bodies to no. Alright. So now all we have left is the rotating region and a wind tunnel. And the last thing I want to do is I want to create a body of influence. Do about the YZ plane. I've already created a sketch for it, but we can recreate it a bit. This dimension is useless. Yeah, let's just recreate that sketch. That's fine. So what we're going to do is create a body of influence, which is basically just a rectangle around the swept area of the turbine, which is just basically set there to increase mesh quality in that particular area. So we're going to decrease the element size in that area, just so that, you know, we might have like an element size generally of about like a ½ meter here, but let's say I just want to isolate this particular region, this rectangular region of the turbine, and I want to make that like 0.1 meters element size for the mesh instead. So that's what the body of influence is going to do. So it improves our mesh quality for us without having to make the entire wind tunnel a smaller element size. So we'll come to the YZ plane, go to sketching again. I'll select the rectangle tool. Just create a rectangle. I'll go a little bit. Let's cancel this. I'm gonna go decent distance. Let's just see how large our rotating region is again. Yeah, I think that's pretty good. That should have good blade coverage. Maybe I'll even make it a little bit longer. Because that way, if you improve the mesh quality in this area too, past the blades also, we can get better quality of the wakes and vortices. Okay, so what else? I'll make sure that this is symmetric about the y-axis, so I'll select the y-axis and symmetry constraints, and then I'll select the top two edges. And that's really it. We can extrude this now. Again, add material frozen, and we'll go to both axes symmetric, and we'll make this just about the width of our rotating region. So say about a meter. What else? That's really it. We can change this to a fluid also, and we can change its name if we want to. I'm just going to do BOI for body of influence. That's it for geometry. So now we can take this and go over to the meshing. So I'm going to just save this. Then close Design Modeler. We'll drag a mesh, drag the geometry in, open the mesh. Okay, we're going to go to the mesh, click on the mesh, physics preference to CFD, make sure it's on fluent. Quality, we're going to set smoothing to high. Select our mesh metric as orthogonal quality, which isn't going to matter yet, but it will soon. And then what we're going to do, insert a sizing. We're going to select our geometry as the rotating region and the wind tunnel as bodies. So select the rotating region and the wind tunnel, and then we're going to select body of influence, and we're going to select that inner body of influence that we created before. Okay, and we're going to make this, since the normal element size is half a meter, we're going to make this about 1/10 of a meter. Next thing we'll do is insert another sizing. This is going to be an edge sizing. Now that we created the body of influence, I can hide the body of influence because I don't want that solid or fluid boundary area showing up in our simulations. So the next sizing we're going to do is edge sizing around the blades. So I'll select all the edges around the blades. Okay. Make sure that this is set to no, behavior set to soft. We're going to make this really tiny. Not that tiny, that's too small. Let's go like 8 to the -4th, 8 times 10 to the -4th. Insert another sizing, and before we do that, let's start making our name selections actually. So now we're going to make our name selections. So we'll do the face selection tool. This is going to be our inlet. These are going to be our tunnel walls. This is going to be our outlet. You can press N to use as a shortcut for name selections. Next we got to select our interface regions. So I'm going to hide the rotating region. I'm going to create a section plane. And I'm going to select the inner region that we subtracted from the wind tunnel, which was the rotating region. Interface, we'll say winterface, that's funny. Wind tunnel interface 1. I'll hide this and we'll show the rotating region. I'll select the outer face of the rotating region. We'll say rotating region interface 1. Okay, and then we can also select the blades. So cool. We can select blades individually, right? So I can do blade left, and I can also do blade right. You can also select them together. I'm not really sure what's best yet. I just figure let me just select them separately, and because maybe I need to do separate calculations. I don't know, but why not be safe, just in case I need the flexibility. So I should have 4 faces here, 4 faces here. I think that's it in terms of name selections. What else? Alright, looks pretty good to me. Now we need to insert our other sizings, right? So this is going to be a face sizing. So we'll then select our faces in the group, add it to the geometry, make this, I don't know, 6 times 10 to the negative third. We'll make this no, change the behavior to hard, and then add inflation. The inflation is going to act on the rotating region, and the boundary is going to be the blades. So we'll select the items in group blades. We're going to go to first layer thickness. I'm going to set the maximum layers to 15. I'm going to make this a really small number. We're going to see if it works out for us, and if not, we'll make it smaller. I don't think that's the best way to create the first layer height. I know there's a mathematical way to do it based on your geometry, but I'm working with what I have for right now, and this works out. So now we're going to create the mesh. So we'll select, generate, sorry, not update. Alright, I changed some settings around, so my edge sizing on the blades is now soft. Set it to 0.0015. Face sizing is 0.008. Inflation is 1 times 10 to the negative fifth. Body sizing is 1/10. Still have all of our name selections. And if we look at our orthogonal quality, so as long as we're above an orthogonal quality of essentially 0.15, we're good. And we see that the vast majority of our cells are above that margin, because this is the 0.15 margin, so this is acceptable or sufficient. And then past that is essentially all the other elements. The only elements that are considered poor here is some of our edges on the blades, but we have a good number of blade edges that are also of good quality, so I believe we're okay. Alright, so that's it for the mesh. And now we can put this in a Fluent. What I'm going to do is actually, because I haven't set this simulation up yet, I'm going to set it up here on this one. I'm going to set up a steady state flow to start. Just going to view the blades because it's what I want to look at right now. Alright. Go to my models. SSTK omega is what I'm working with. That's the general model that's applied to any Fluent project. I'm going to go to my rotating region. Frame motion, because we're in steady state right now. In the Z direction, and I'm not going to apply a rotational velocity yet because we're just doing a steady state case, and I'm going to act like this is a static rotor to start. Okay, go to boundary conditions, go to inlet, change this to velocity inlet. I'm going to do 2.71 meters per second because that's just what I'm deciding to work with right now. Okay, outlet is a pressure outlet, and it should already be set to 0, and it is. reference values, we can compute from the inlet. That'll only give us the inlet velocity. We need to do the area and the length. Area is the area, frontal area of your turbine. So frontal area, whatever. So it's going to be this blade face and the area of this blade face. So I know that this blade face is equivalent to 1 foot squared, which is 0.09290304, if I'm not mistaken. Yes. Okay. And then my length, in my case, is going to be, give me 1 second. So 0.3048. Oh, excuse me. This is only the, so this is the area of just this blade face, but I also need to include this blade face. So in my case also, well, first of all, the turbine diameter is going to be a foot plus this 3 inches of distance that we have here. So this is going to be 0.3048 times 2, which is going to be 0.6096 meters. And then we're going to add this 3 inches of distance. And since 1 inch is equivalent to 0.0254, we'll just add that on to 0.0696. So my diameter or length is going to be 0.6858. Oh. Yeah, that's correct. Okay, and then I now need to add on the area, the frontal area of this turbine. I don't think that's correct, actually. Let's double this. I want to see what happens if I double this area. Well, nah, let's double it. Because it's really supposed to be like the swept area of the turbine. So, let's double that. Maybe that's why I was getting such large coefficient of drag values in my other simulation. 0.929.304 times 2. 1858608. Okay. Alright. Now we can initialize the solution. Well, first of all, let's go to methods. Coupled pressure velocity scheme. I'm going to do higher order term relaxation. I'm going to come to controls, not change anything here. Port definitions, this is where we're going to want to create force reports of drag. So I'm going to do coefficient of drag, coefficient of lift. In my case, it's going to be in the Y direction on the blades. Force of drag on the blades in the Y direction. Coefficient of lift on the blades in the Z direction. Force of lift in the Z direction. Tau in the Z direction on the blades. Okay, go to residuals. Bump this down by order of magnitude. And we're going to initialize using hybrid initialization. Alright, and this converges for sure. Now we can create a plane. At the axis. And then create some contours. So we'll do a pressure contour on the blades using also the plane, and then we'll also create a velocity contour on the blades and the plane. Cool. We can also create path lines if we want. I don't really know if they're that useful, but we'll use them. $500 steps is a lot. We could probably bump this down to like 250, or I can do path skip. Yeah, that's a lot. Looks cool though. That's actually not that lot. That's not that much. Let's draw the mesh though too. All right. Um. 500 steps. That's not that many. Looks like there used to be a lot more. Well, this is also just the initialized case. That's fine. We can create an animation for the path lines if we want. 500 steps is a lot. Let's do 300 steps, just for the sake of it. All right, and we can close it. Alright, last thing we'll do is I'm going to go to calculation activities, solution animations, and I'm going to make the path lines an animation. If this was a transient simulation, I'd also make the contours a simulation, or an animation, but it's not, so I'm not worried about that right now. That's it. We'll do 300 iterations just to see if it converges in that case, and if it doesn't, we'll keep going. And that's the setup. For a transient simulation, I'd add a couple extra report definitions, like power of the turbine and power of the wind, and a coefficient for eta. Yeah. See how long this takes to converge. And you'd also just go to general. You'd set your model from steady state to transient. We'll go to our cell zone conditions. If you prescribe if you had a prescribed frame motion from the steady state case, you'd press copy to mesh motion, and that would really be it. And then you'd have to, when you run your calculation again, of course, change your time step size and your number of time steps, and then run the calculation. All right.